and then I'll upload. But
I want it in my notes.
yeah,
I want a letter.
it didn't say the recording is in progress. Let me just make sure. No, my sound is off, so it's okay. It's okay. Yeah, it's like blinking. It doesn't say stop recording on here because I'm on share. No.
Yes.
Yeah.
stop.
Yeah, but it's blinking though. See, look down here. That means it's recording. Can you see that?
Barely.
Barely. Yeah. That's how I know it's recording. Okay, go away. All right. Okay, so we're going to use our Biot-Savart law, of R, is mu 0/4 pi. And then we're going to use it for surface current because this guy has got a surface current. I'll explain in a second, but I'm going to write this down first. We have K, the surface current density, cross omega hat, dA. This is the Biot-Savart law for surface currents, right? Okay, all right, and then we're going to be to find the magnetic field inside and outside an infinitely long solenoid of radius r, okay, with n turns per unit length, carrying a steady current I. Okay, so this picture is not really quite complete because what really is happening is that there's, like, think of it like very thin wires that are, wrapped around here. Let me use a different color. That are wrapped around the solenoid. Okay? Very wrapped around. And so the current is flowing on the surface, but because it's wrapped with wires. Does that make sense? Okay. Let me see, my eraser will actually erase here, or is it going to erase the figure? Oh, okay. Okay, so, but we're just going to think of it as a surface current. Okay, so what we're going to do is we're going to put the field point on the x-axis. That's where this point is right here. So we're going to have the field point right here. It's going to be a, yeah, worry about it. And then we are going to look at a little patch of that current that's up here. Patch of current, right? With area dA. Yeah. Okay. And we're going to try to do the pedantic approach to figure out all the things. Okay. So first of all, we can draw, let me move my Copic color thing up here. We can draw R that goes from the origin, okay, to the field point. So that's R, right? And I can write R as just S0, 0, or if you prefer S hat. If you prefer, S hat, right? Okay. And then let's look at R prime. So remember that R prime goes from the origin to the source, which is going to be here, right? Try not to draw over our omega right there. It's really blurry, but okay, this is R prime, right? Okay, so let's think about what R prime is. So think about the fact that R prime kind of sticking. So imagine it's a cylinder. R prime is kind of just sticking out into space, right? So it has a component along the x-axis, the y-axis, and the z-axis. The z-axis, it's just z, whatever z is. It's going to be z hat, right? Okay, But on the x-axis, you can see because it's got a perpendicular kind of dropped down here, right? Does that make sense? It's got a little perpendicular here. That it's going to be, so r prime is going to be just r cosine phi, right? That's phi, in the x hat direction, plus r sine phi in the y hat direction, plus z hat, right? Pretty simple. Okay, now, omega, so this is omega that points from the patch to the field point. Right, so that's omega. They've drawn an omega on their script R thing, but it's harder to see, I feel like. So, and all we have to do to get omega is just, we don't have to think about the geometry because we just do the vector subtraction of R minus R prime. Yeah. Okay, so that's nice. So let's see, we have R is S in the S hat direction. And so we have to think about, well, yeah, I shouldn't have written this S hat. This is not good. My bad, I think, guys. Because I'm using this vector notation, I should have used it correctly. So this is, it's S in the X hat direction and 0 in every other direction, right? Okay. So for our R, we're gonna have, from R, we have the S, and then from the R prime, we're gonna have minus R cosine phi, and that's all in the X hat direction, right? And I'll put that in pink, actually. Okay, and then plus in the Y hat direction, we just have the contribution from R prime. Oh, it's gotta be negative, right? Negative R sine phi in the Y hat direction. And then the Z, we again have negative, right? Because it's the comes from the R prime minus Z in the Z hat direction. Okay, that's great. So that makes everything very easy. Okay, so let's go to another layer. Well, okay, we will need to look back at the picture. I don't think we need it right now to keep going. Well, let me write down K first because K, let's write down K and DA first, right? Before we like dump the picture. Okay. All right, so think about K, right? So look at K here. Have they drawn K, right? So it's kind of a circular current, right? Because it's the wires, it's the wires. So what unit vector is in the direction of K? Or a combination of unit vectors? Phi hat, absolutely, yes. So K, let's see. Now, okay. K is just whatever K is, right? The value of K in the phi hat direction. But we've been using X hat, Y hat, and Z hat. So let's just, we know that we can go look up what phi hat is in terms of X hat and Y hat, right? And so it's actually K times negative sine phi X hat plus cosine phi Y hat. Okay, so that's what K is. Cool. What about DA? Okay, so let's think about DA, right? So the patch is along the surface. So what's changing is phi and Z, but not R. So I know that DA has to be, DA is going to be DL phi DLZ. And I know that this is just R D phi DZ, right? Capital R because we're on the surface of the cylinder, yes? Y'all agree with that?
Yeah.
All right, so I'm going to copy this layer. And we're gonna turn off the figure and turn this off and erase. Okay, I'm gonna erase this. We'll keep our Biosavart law. We're gonna need omega to do stuff. We don't need these guys anymore, though. Okay, so let's do it. We have to get omega, the length of omega, and we have to get omega hat. Right? Well, omega hat's simple because I'm not actually gonna write it out to do the cross product. So in other words, omega hat. So let's do that. Where's my library? What happened? Oh, it just went down here. Okay, so omega hat is going to be just omega, of course, over the length of omega. And that's just going to be S minus R cosine phi over omega x hat minus R sine phi y hat over omega, and then minus z hat over omega. Okay, so I'm not going to write out what omega is. Let's figure out the length of omega. Might as well. It's going to be the square root of S minus R cosine phi squared plus R squared sine squared phi plus Z squared, yeah. And expanding this guy out, we're going to have the square root of S squared plus R squared cosine squared phi minus 2SR cosine phi plus R squared sine squared phi plus Z squared, right? And we finally get S squared plus R squared plus Z squared minus 2SR cosine phi. Yeah, it's ugly, definitely ugly, but there it is. Okay. All right, now we can do the cross product, right? So we're gonna do K cross omega hat, and I'm gonna have X hat, Y hat, Z hat. And in the X hat direction, K is negative K sine, I better expand this, it's too small. Y hat, Z hat, there we go. K sine phi. And in the Y hat direction, it's K cosine phi. And it's 0. And then omega hat is in the X direction, S minus R cosine phi. And then in the Y direction, minus R sine, I still didn't make it big enough. And in the Z direction, negative Z. Okay, sort of got it. All right, so this is going to be, of course, looking at the the X component. It's going to be negative K negative KZ cosine phi, right? Minus 0, so there's the X component. And then minus the Y component. Oh, and I forgot the over omegas on these guys, so this is all over omega. So I will put everything over omega, okay. In the Y component, right, we had to put a minus sign in there. We get kind of a bigger thing. We get KR, so this is an R. Yeah, so positive KR sine squared. And then minus K, and that's over omega. K cosine. Well, I do not have room. Okay. Minus, huh? Yeah, sorry, I'm messing that up, I think. Okay, let's do, yeah, we have to cross those out. Okay, it's K, it's positive KZ sine, right? Over omega, okay? And then minus 0, okay? All right. and then plus the z hat component, which is the one that's ugly. So we have KR sine squared phi over omega, and then minus K cosine phi S R cosine phi over omega. Yes? You okay with all that? All right, so I'm going to get rid of this. We have to remember what DA, we'll just go back to the previous layer for what DA is. Yeah. Okay, and let's do a little simplifying. Okay, so we have negative KZ cosine phi over omega in the x hat direction. We have negative KZ sine phi over omega. Let me double check. KZ sine phi, yes, over omega in the y hat direction. And then in the z hat direction, so we have KR sine squared. We're going to get KR cosine squared with the positive sign. So I'm just going to get KR. KR, right, for these two terms here, this term and this term, yes? And then I'm going to get minus KS cosine of phi, yes? All over omega in the z hat direction. Yeah? You good with that? Okay, now we should do some reasoning, because if we go back to the picture, why are you, oh my God, stop. It just won't move. Okay, so we go back to the picture, right? We can see that, you know, we have an X component, we have an X hat component, a Y hat component, and a Z hat component. Which one do you think survive? Given the symmetry.
Let's see, part just this.
Yeah, because the X hat, if you go, so here we're taking a patch here, but if you go to a patch on the other side, right, you're gonna get, cancel it. And then on the Y, there'll be a component here, but if you go to the other side, that will be a negative side. And then you'll component, but the Z's are gonna add up.
Yeah.
Okay, all right, so we're gonna just kill those other, again, you can always prove it to yourself by actually integrating it up, right? Okay. Okay, no, my bad. Here we go. Okay, so now we're gonna have to get another layer and continue our work. Now the integrals are the nasty parts. Okay, so let's duplicate our layer, turn this guy off. And we have our cross product, and we know we only need to keep one piece. And we can now set up our integrals or integral. Well, they're all two of them, right? There's, because it's dA. I'm just gonna erase these two components. Right, and I'll write it all down in terms of the integral in a second here. Write this. I want to use the one that's already. Cross. So let's do, this is equal to mu naught over 4 pi. And remember that dA was equal to R d phi dz, right? Okay, so we have, the first thing is the cross product. I can pull out a K. So I'm going to pull a K out here, right? dA has an R that's constant. I'm going to pull out the R, right? Good with that? And then we can write down what the integral is. So the integral is K cross R is R minus S cosine phi over omega. Yeah, over omega cubed, right? Which is S squared plus R squared plus Z squared minus 2SR cosine phi to 3/2. Okay, and this is over d phi dz. Okay, so the limits of the integral for phi are 0 to 2 pi. For z, it's negative infinity to infinity. Yeah. Okay, so here's where it becomes just, unfun. First, we've got to figure out what to do, which integral to do first. The z integral actually is a lot better than the phi integral. If you tried to put this into, Mathematica maybe would do it, maybe. Wolfram definitely not. So, and looking it up is just terrible, the phi integral. So the z integral we can deal with for now. What are you thinking, Shauna?
Find where the R and D is.
Here. Okay.
Yeah,
I was looking at the R minus S.
that came from the cross product.
Yeah.
Yeah.
Oh, and then of course we have a z hat out here.
Okay, yeah, yeah. Follow.
Okay. All right. So I'd say we do the z integral first and we write it as, so we have z hat mu 0 k r over 4 pi. And then we're going to have the integral, and we're going to pull r minus s cosine phi. Notice we're not integrating over s, right? Out, and then I'm going to put the dz integral here from negative infinity to infinity. And that is dz over z squared plus d squared to the 3/2, where I'm just grabbing everything and putting it into d squared. So that's d squared is going to be s squared plus r squared minus 2sr cosine phi. Kind of the law of cosines piece. Yeah. Okay, and this and this, of course, there's a d phi out here, right? 0 to 2 pi. Okay, but I'm just going to do this guy right here. All right, so this integral, so actually, let me outline that in pink. Do that in pink. So in pink, we have our integral negative infinity to infinity, dz over z squared plus d squared to the 3/2. This is something that you can look up. All right, now it is an even integral, so there's no reason, it's even in z. There's no reason why I can't integrate from 0 to infinity instead. With a 2 out in front. So 2 times the 0 to infinity integral of the same thing. Okay, and so this becomes just, let's see. Yes, 2, yes, okay. It just becomes 2 times z over d squared, and then the square root of z squared plus d squared. And we evaluate that between 0 and infinity. Okay, so just like we did before, we got to do a little work. So the first thing we would do is notice that when z is 0, that thing is 0. So we know that one of the limits will give us 0. The infinity limit, however, we just got to do a tiny bit of work, right? So we're just going to pull out this z squared. So I'm going to go. So I know that the 0 limit gives me 0. So I'm just going to leave him off. He's just not there. So we get 2z over d squared z, 1 plus d over z squared to the 1/2, right? The z's cancel here, and I just get 2 over d squared. And then 1 over 1 plus, and this is at infinity, sorry, at infinity, d squared over z squared, all to the 1/2, right? At infinity, and at infinity, this term here goes away, right? It's 0, and I just get 2 over d squared. And we know the limit with the 0 is 0, so the whole thing is 2 over d squared. Yeah?
Yeah.
Okay, let's put it back in. I will erase, if everyone's ready. Okay. Okay, so this gives us equal to z hat mu 0 k r over 2 pi, because I'm just putting that 2 in. I can't pull the d squared out. That's got a cosine theta, I mean phi, so I can't pull it out of the integral. It's in the integral, right? It's in the phi integral now. Okay, so then we have 0 to 2 pi. And now we have r minus s cosine phi on the top, d phi, and then on the bottom, we have d squared, which is just s squared plus r squared minus 2sr cosine phi. Okay, so there's no square root or anything anymore, which is nice, at least, at the very least. Nice. That's a nice thing. Okay. Okay, so this is not easy to look up either. Try to do it in Mathematica, gives you a little bit of nonsense answer, sort of hard to interpret, I gotta say. But we can transform this, and that's what we're gonna do next. Okay, so let me copy, did I already copy this layer? But I'll copy it again. All right, so I need to figure out this thing. So what I'm gonna do is I'm going to come back to this layer in a minute. But what I'm gonna do is, actually, no, let me just get a full layer, new layer, and we're just gonna look at r minus s cosine phi. Now I can write this as 1 over 2r, right? And then r squared minus s squared plus r squared plus s squared minus 2rs cosine phi, which of course is our d squared, right? But notice that this would work out to exactly this, right? So pull this, you notice that the minus s squareds would cancel here, right? And here. And then notice that when you pull the 1 over r, you get an r here and r here, right? That would add up to 2r, but then the 2 cancels. And then the 2 would cancel this and the r would cancel and you'd get this back. It's exactly the same. Okay. Why is this helpful? May not think it's helpful, but it actually is. So let's go back to our layer. Okay. And we're going to write this out. And hint, hint, there is a much easier way to find the field that we're going to do on Monday, which is Ampere's law. Kind of like Gauss's law is a much easier way to do the electric fields. You remember that nasty sphere problem we did? This is the equivalent. Okay. All right. So we'll have mu 0 k r. And then over 2 pi, but then we have 1 over 2r because we're replacing this r minus s cos was our other thing, okay? 1 over 2r, and then we have the r squared minus s squared does not have to be inside the integral, lucky. And so we have two terms here. This term here, which would just be d phi over r squared plus s squared minus 2rs cosine phi. That was our original thing. And then plus just a term that looks like this. 0 to 2 pi d phi. Okay, that's what we get for doing that, which is a lot better. Just a lot better. Right? Do you agree? Okay. This you can look up, right? This integral here with this cosine theta, you can look up. It's not pretty, but you can look it up. Okay, and I'm going to transform it one more time before we look it up. But let's put a box around it. Take a look. Okay. All right. Okay, so let's do the integral 0 to 2 pi of d phi over r squared plus s squared minus 2rs cosine phi. Okay, now we can write this in terms of an integral that looks very similar. So notice that, well, let's go to, I feel like I don't have enough colors. I don't understand. Okay. Let's look at the integral 0 to 2 pi d phi over a plus b cosine phi. This is easily looked up. Okay. We can rewrite it one more time to 2 times the integral from 0 to pi because cosine is an even function. D phi over a plus b cosine phi. And then I can actually do this and kind of look this integral up. This integral is 4 over square root of a squared minus b squared. And then the arctangent, fun times, of the square root of a squared minus b squared over a plus b. And then the tangent of phi over 2, and that's between 0 and pi. Sorry, very bad. Okay, let's actually execute that. And then we'll calculate that a squared and all, because you can see here that a, right here, how about this? A is this, and b is negative 2rs, sorry. Yeah? Okay, anyway, we'll calculate in a second. Let's just execute the limits. Square root of a squared minus b squared. Okay, now the limits here, we have the inverse tangent. I'm doing the first limit, which is pi. Square root of a squared minus b squared. And then tangent of pi over 2. Okay, don't freak out. I know tangent of pi over 2 is undefined. And then inverse tangent of 0, right? That's the next thing. Right? Oops, sorry, my bad. Here we go, like this. Okay. Yeah? You good with that? Inverse tangent of 0 is 0, so we're good with that. Okay, yes. So it's only that first term we have to worry about. Now, the tangent of pi over 2 is undefined, but the inverse tangent of undefined is just pi over 2, right? Yeah. So this becomes square root of a squared minus b squared pi over 2. Okay, much nicer. And then we can write it one more time as 2 pi over the square root of a squared minus b squared. Yeah. Okay, now we just got to figure out the a and b, because the a is that r squared plus s squared and the b squared, blah, blah, blah. So let's calculate what we need. We need a squared minus b squared. Okay. So that's in yellow. Well, no. A squared is going to be, so my bad here. A squared minus b squared equals, and then we have a squared, which is r squared plus s squared all squared, and then plus, or sorry, minus b squared, which is going to be 4r r squared s squared. Yeah? Okay, now we're gonna square it out, and I'm gonna drop the color coding. Okay, r fourth plus s to the fourth minus two, probably plus two r squared s squared minus four r squared s squared, which gives me r to the fourth plus s to the fourth minus two r squared s squared, yeah? And then I can rewrite this as r squared minus s squared squared. Correct? Okay, well, that's really not bad. So now our integral in green is 2 pi over well, okay, we got to be a tiny bit careful. Yeah, because we're taking a square root, something squared, that's fine, as long as whatever's in there is not negative, or we have to put absolute values in front of, on top of things, right? Just gotta be a little careful. So r squared minus s squared. Yeah, square with the absolute value signs. Now we put our point inside the solenoid, but there was nothing about that calculation that meant that it had to be inside the solenoid. So s can be outside the solenoid. And in fact, we'll take those two cases. That make sense? Yes. Okay, back to our total integral. Okay, so back to, where was that layer? I'm going to confuse myself in a second here. Okay, I think I can do this. All right. So I'm going to do this by erasing. We just did this integral, right? And we found that this integral was 2 pi over the absolute value of r squared minus s squared, correct? I'm not missing any constants or anything, right? So let's erase, and oops, my bad. And this becomes 2 pi over r squared minus s squared absolute value. Okay, and then this integral is super easy to do. It's just 2 pi, right? Okay, now time to erase the rest of this. And keep going. We're almost there. Shoot, I didn't mean to do that. I didn't want to erase that bottom part. Go away, damn it. Okay. Thank you, because I just messed it up.
Let's see that.
Okay, hold on. B. Mm-hmm.
You know, AR 2 pi.
And then 1 over 2r. Oh, and then our stuff. Okay. And then 2 pi can come out. 2 pi. Give me a second. I'll deal with all those constants in a minute. Okay. And then r squared minus s squared over r squared minus s squared absolute value plus 1. Okay, and now one more time. Z hat. We get 2 pi r mu 0 k over 2. Yeah. R squared minus s squared over absolute value of r squared minus s squared plus 1. Okay, now it's time to decide whether we want to be inside or outside of the solenoid. So inside. Okay. inside, R is less than S. I'm sorry, S is less than R. Okay. If S is less than R, then the absolute value I just take the absolute value sign off, right? And I get B in is equal to Z hat mu 0K over 2. And then I get R squared minus S squared over R squared minus S squared, which is 1, plus another 1, which gives me a 2, which just gives me Z hat mu 0K. Okay. Outside, S is greater than R, and that means that absolute value has to switch signs, right? So we get B out is equal to Z hat mu 0K over 2, and then we have R squared minus S squared over negative R squared minus S squared. In other words, and then plus 1, in other words, 0. Okay. One more thing is just to notice that K is equal to just the number of turns times the current in that turn, right? So we could replace all the Ks. So finally, we have B in is equal to mu 0 Ni in the Z hat direction, and B out is still 0. Yeah. Fun. Luckily, we have Ampere's law coming up on Monday. We'll never have to do something that horrible again. Yeah. All right, that's it, guys. That is it.